What's up, guys? I'm streaming. I just thought I'd start recording as well. I'm going to be watching several videos on particle physics from this series. They seem pretty good. Let me go back.
To quarks, charge of quarks, strangeness of quarks, and we're going to finish off with a summary. So first of all, we're going to introduce the idea of quarks. Hadrons are a class of particle that include the proton and the neutron. So we've already come across the group of particles which are called the hadrons, and we've seen that two examples of hadrons are the proton and also the neutron. So both these particles are classified...
Okay, so I'm going to be honest, even as someone claiming for 8 years to have discovered the theory of everything, I am coming from a pretty basic standpoint when it comes to the specifics of quantum mechanics. I have been looking into this recently, and I'm trying to get a grasp on what's going on for several reasons, because I think there's things that can be gleaned, although I don't agree so far with a lot of things, which I'll mention. But like, for instance, I find this, so like protons and neutrons, I know those things. Hadrons, it's a little confusing because we've already, as it says here, are a class of particles that include the proton and neutron. So what else would be a hadron if not just a proton and neutron? Most of them. Why is it doing this? I don't want it to be highlighted. It's like distractingly highlighted. That's a little better. Hadron is a composite subatomic particle made up of two or more quarks held together by the strong interaction, analogous to molecules held together by the electric force. I find that interesting. If quarks are so, then that's real interesting. So essentially, hadrons, baryons, and mesons. Okay.
As hadrons. Different hadrons vary in their properties, such as charge and rest mass. So we can compare the charge of protons and neutrons. So here we have a proton and here we have a neutron. So we know that the charge of a proton is equal to +1. It's got a positive charge. And we know that a neutron is neutral, so it has 0 charge. And we can also compare their masses, because in fact, although they've got very similar masses, their masses are slightly different. So a proton has a rest mass of 1.673 times 10 to the minus 27 kilograms, whereas a neutron has a rest mass of 1.675 times 10 to the minus 27 kilograms. So they've got slightly different rest masses and they've got different charges. But if they're both classified as hadrons, why do they have these different properties? These differences can be explained by assuming hadrons are made up of smaller particles. So if we were to take a closer look at a proton, we'd find that it's actually made up of smaller particles. So we've said that hadrons aren't fundamental particles, which means that they can be broken up into smaller particles. So they're made up of other particles that are...
This is where I really find there to be a high probability of a major misunderstanding occurring. Because, yeah, they're made up of smaller particles, but it doesn't mean they're made up of 3 particles. They're made up of smaller particles, more likely, in the same way as Earth is made up of atoms. And so a proton is made up of smaller particles, like atoms of the Earth. Wouldn't resemble this like 3 quark thing going on in the proton and neutron. And various other quark setups have been coming across. But as we see here, assuming hadrons are made up of smaller particles, and not just assuming they're made up of smaller particles, but specifically this kind of smaller particles, quarks, and the basis of the quarks being that there are differences in the particles and various other reasons. But that there is an assumption of these particles, and on top of it, they've literally never been observed, is suggestive that this is something that got through like to consensus without being under the rigors of scientific debate that would have prevented it from being so accepted, in my opinion. The quark concept seems a little too accepted. There's all sorts of explanations for why systems would have different masses without them being composed of specifically 3 particles in this way. And then even the thing is, like, I like the concept that there's particles within the 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 particles all the way down, and that like sometimes they break out and so they get released from inside the particle. And so there probably are particles within the particle, but they're probably not as described by the quark system. That's my take so far. I just am pausing to point that out because of this assuming, and I think it is really important that this has literally been from the beginning of the process an assumption that there are quarks, and even, yes, they fit the observations in ways where we can see that there are patterns, but they still don't require the explanation of quarks, and there's so much to it that's going on. Okay.
Smaller. Whereas leptons that we've previously encountered are fundamental particles, so they can't be split into smaller particles. And we call these smaller particles quarks. So the particles that make up protons and neutrons and other hadrons are called quarks. So although protons and neutrons aren't fundamental particles because they're made up of smaller particles, these quarks can't exist in isolation. So they must be combined in order to form other hadrons. There are 3 types of quarks, referred to as the first generation quarks, termed up, down, and strange. So here we can see we've got our different quarks. So our blue circle...
This is so common in quantum mechanics that we just jump into that there are quarks. We assume they are, and then we just... there are. Common problem I face when I encounter this is they're just maybe that's how it occurs, because I, in reflection, do the same things. But I present a line of reason because I understand the importance thereof, and I think it's like underpinned in the way quantum mechanics presents itself, where there is no need to explain itself at the first steps, and it just starts. It's like we were, like born into a life, and then we went through all these things where we learned all sorts of stuff, and now we're supposed to just ignore it all and just say assume, and then go from assumption and literally forget we made an assumption, and get so deeply ingrained in the like what comes after that assumption that we, oh yeah, all this other stuff is clearly true, because we're so far past the assumption that we're not even noticing it anymore. It's so far back there. Hello, assumption. I see it. Here's an assumption. Let's remember that.
Circle represents the up.
Not that it's not touching on and
Quark. Our red circle represents the down quark. And finally, our yellow circle represents the strange quark. So these are the images we're going to use for quarks throughout our videos. We can represent these quarks with symbols. So for our up quark, we use a U. For our down quark, we use D for down. And for our strange quark, we use an S. So these are the symbols we use for the different quarks. And we've previously encountered that all particles have a corresponding antiparticles, and this is also the case for quarks. So each quark has a corresponding antiquark. So we have the anti-up quark, we have the anti-down quark, and we've also got the anti-strange quark. So these are all antiquarks. And their symbols are the same as the symbols for the quarks, but with a bar on top to show that it's the antiquark. So we've seen that.
I feel like it's not worked out as rigorously. Like, it's not a textbook. Like, textbooks in a more basic science, because this is complex and still kind of fluid and not worked out so rigidly, where it is almost like A, B, C, D, E, F, G, like a sequence of presentation that's just like every chemistry teacher in the United States and in the world generally follows this order of presentation of the information to build on this like structure that has been worked out across a long enough time, where the presentation sequence can take us from like arithmetic and basic skills and come to a point of like truly grasping the subject matter. And then this says, we didn't know what we were talking about. Forget it all. Forget it all. That's not how it is. This is how it is. And so there's quarks. And then there's an up quark, there's a down quark, there's a strange quark, there's anti-quarks. Yes, there's basis for these things observationally in terms of there are nuances of the nature of reality that are observable in these ways that we then interpret through this lens, but that doesn't mean the lens is like the lens of reality. It may just be an approximation. And it almost inevitably it is, because it's built off of a foundational line of reasoning that there are such a thing as elementary particles. And so they said, well, there's too many elementary particles. We're finding too many particles. There must be some true elementary particle of which all these particles is composed. That would make it simpler. And in that way, the real truth is that everything is actually built from this one elementary particle. And that's simpler. And so they try to do that because it makes sense in some ways. When we are taking the assumption path that there is such a thing as an elementary particle, which is essentially saying that as particles get smaller, they get simpler in complexity, when the reality is they're all equal in complexity, because the universe is infinite. And so there is no end to how large or small particles can be relative to one another. But also there's no requirement within an infinite array of particles for an observer to be composed of the particles that we're composed of. They can be composed of any particle, and that will then change their perception of reality in a way where they will see the nucleus of an atom that we see as a nucleus of an atom, as a star. They'll see it as a black hole. All things are relative, as above, so below, the principle of correspondence. So when I come across this quark concept and see the line of reasoning is A, there are such things as elementary particles. Simpler is smaller, when the reality is simpler is harder for us to see. So it's actually more complex in terms of more approximations, and to the point where it literally becomes spin, charge, and just basic quantities of measure of something we deem as like a separate and distinct system, like an atom. Versus when we look up and see, oh, there's Jupiter. Like, it's not the same as Mars, or as Venus, or as Mercury, or as Saturn. Isn't that interesting how they're all not the same? But in our small perception, in our perception of the small, it becomes that they are all the same as electrons. There's quarks. And notice, they're not all the same, so there's subtleties amongst them. So now we gotta have the up and down quark, and so even the quark, which is aimed to be an elementary particle, is really an array of particles, like the periodic table of elements. And maybe that's something that happens, is there's certain like ranges of stability that are like spikes. That stability occurs, and then around it there's smaller spikes that are more short-lived and not as stable. And then there's like a drop-off where there's just nothing going on, and then another portion of the same repeating thing where there's spikes for like some like optimal equilibrium that basically forms the periodic table, for instance. I do believe, though, that there are protons, even if there's like Earth is the nucleus of an atom. Like, where are its protons and neutrons? or any system out there. If that's the case, where are they? And I think maybe they still are the case, even, and they're just hidden from us, like within the planet, literally spinning around one another. And then when the certain like energy of the ethereal particles, flows of energy going on there change because of more macroscopic changes, like a light bulb turns on and shit, the whole cosmos is lit up by this light bulb suddenly. If we live in this tiny spot and then suddenly the light's on, it's kind of whoa.
Quarks make up protons and neutrons and other hadrons.
But so, like, if the energy flows within the planet change, maybe it can shoot out some, like, array of smaller particles that are, like, the next level down kind of things that then are swirling around at the center of the Earth and can literally shoot out the planet and come out the planet. Like the decay of the particle. Which I think might have happened if we look at the Pacific Ocean. I don't know. When the Earth expanded, it basically underwent a decay process. Some tangent. When the Earth expanded, not plate tectonics, but the Earth was a single landmass, and it fractured at the Mediterranean and went west, and then it went between South America and North America. We can tell this because of the age of the ocean floor, which is dated using the assumption, just like this assumption, that quarks exist. The assumption that quarks exist. Literally, assume quarks exist. Then so we can tell, though, the oldest ocean floor, because it's still occurred in a way when the Earth expanded, where it fractured rapidly, and then the oldest ocean floor is where it began. And then it basically went west along the Mediterranean, and then everything was still connected, and down when North America and Africa are still together between them. And then it went west into the Pacific. And then somehow this fucking thing happens here. I thought maybe like this crack reaches the Pacific, which maybe the South Pole was here, and it explodes, because it fucking exploded. The Earth exploded here. That's why there's a ring of fire in the Pacific. That's why it's nice and neat everywhere else, and the Pacific is just chaos in a fucking huge ocean. Pardon my language. Pardon my language. But maybe like literally a particle is ejected from the Earth here. It just flies out of the Earth, shoves Australia this way. Away, because it was up here. It's connected to Asia. Shoves debris this way, literally creates the Indonesian archipelago, because I'm pretty sure this was all created in the process. And then, but maybe that's what happened. Why was that?
And we've seen that.
So maybe there are these particles like protons and neutrons within the planet that make the planet be a atom having like whatever it is on some other level of existence where it's like 42 protons or whatever, maybe, and however many neutrons. And therefore, it is that particle on another level of existence. And so maybe when it decayed, it shot off one of them, literally exiting through the planet itself. And maybe part of what was going on as it was doing that, it was causing the Earth to crack. I'm not sure why it would be rupturing here after a crack occurring, and then like the object is emitted, if such a thing occurred. Or is absorbed. That'd be fucking crazy. Oh no, it wasn't emitted, it was absorbed. No. I think it was emitted. Because the Earth itself decayed. That's essentially. I know I'm getting on some crazy tangent and therefore, like, what the fuck? I was just watching a reaction about particle physics that seemed generally sane.
Different hadrons actually have different charges. So we're going to see how the charge of quarks can actually affect the charges of protons and neutrons and other hadrons. So each quark has a characteristic charge. So for example, here our up quark has a particular charge. These charges are all some fraction of the elementary charge. So if we're looking at our up, down and strange quarks, they've each got a charge, and each of their charge is a fraction of the elementary charge. So for example, the up quark has a charge of plus 2/3 of the elementary charge. So it's not a whole elementary charge, it's only a fraction. And then the down quark has a charge of minus 1/3 of the elementary charge. And the strange quark...
I hope the mere fact that they have fractional charge is sufficient to just be like, no. Oh, that would be so much easier if this was all just literally wrong. Oh yeah, quarks don't exist at all. Oh. They are just useful tools to explain like the flows of energy that are occurring, but they don't actually exist. It's simpler in some way, but also more complex. It's like it has an intermediary. Like they literally create an intermediary, like the W boson decays and then it becomes two particles, but I'm not sure we even observe the W boson, but it's used as evidence for the quark's existence indirectly, even though it's not even directly observed. I'm not sure what's going on, and I also I'm a little concerned by the proof of particles existing by seeing flow patterns in particle collisions. Like, see this? This here is a M, or whatever. Sorry. Let's go with muon. This is a muon based on the way the particle flows. Period. Doesn't end the story. There's no possible other explanation for what could be going on in a more classical sense without introducing just an array of particles. It's so exhausting, guys. I know I'm probably exhausting.
Also has a charge of minus 1/3 of the elementary charge. And we can add the charge for the different combinations of quarks in hadrons to give its overall charge. So for example, here we've got a number of quarks making up a hadron, And if we add together the charges of these quarks, we can get the overall charge of the hadron. For example, we can add the charges of the quarks in a proton to find its overall charge. So let's look at the quark composition of a proton. We can see that it's made up of two up quarks. So the charge of an up quark, we've said, is equal to plus 2/3 of the elementary charge. And then this proton is also made up of one down quark. And we've said that the charge of a down quark is equal to minus 1/3 of the elementary charge. So we can add these charges together to get the proton charge. So the proton charge is going to be equal to 2 times the charge of the up quark, so 2 times 2/3 of the elementary charge, and that's because we've got 2 up quarks, plus the charge of the down quark, which is in fact correct. We know that the proton charge is plus 1 of the elementary charge. We can summarise the relative charge of each quark in a table. So if we're looking at the relative charges, the up quark has a charge of plus 2/3. The down quark has
a strange 0. We don't need it to explain anything with regard to charge, so we need to just be 0.
Charge of minus 1/3, and the strange quark has a charge of minus 1/3 as well.
Okay. Pardon me.
An antiquark has the same magnitude of charge as its corresponding quark, but the opposite sign. So that means for our anti-up quark, we're going to have a charge of minus 2/3. So the magnitude is the same 2/3, we're just reversing the sign. For our anti-down quark, we're going to have plus 1/3, again same magnitude, opposite sign. And for our anti-strange, we have plus 1/3 as well. So the final property we're going to and for our anti-strange, we have plus 1/3 as well. So the final property we're going to look at that's related to quarks is something called strangeness. Some quarks have an additional property we are interested in called strangeness. So strangeness is a property just related to a magnitude opposite.
So strange particles are also charge-wise equivalent to down quarks. Okay, so there is that going on.
To quarks is something called strangeness. Some quarks have an additional property we are interested in called strangeness. So strangeness is a property just related to quarks, and we will look into it in a lot more detail in a later video. Only strange quarks and antiquarks possess strangeness. So here we have our strange quark, and here we have our anti-strange quark.
I do not like the consistent, habitual, only where convenient does something occur in quantum mechanics.
And these are the only quarks that possess strangeness. Unlike charge, the strangeness of a strange quark is negative, with a value of -1. This means the strangeness of a strange antiquark is positive, with a value of +1. So again, going back to our strange...
So these are down particles, basically. I'm just going to say that. Whatever. They're equivalent to down charge-wise that have some other characteristic going on that we then labeled as strange. I would prefer it not to be utterly detached from down, though. At least there must be some benefit to recognizing they have the same charge and probably the same mass. Just this additional feature that isn't necessary to explain some things coming up.
And anti-strange quarks.
seemingly theory-based a lot of the time.
We've said that a strange quark has negative strangeness. So its strangeness is going to be equal to -1. Whereas the strangeness of its antiquark is going to
Oh my god, I hope this makes sense.
be equal to +1.
Strangeness.
So the strangeness of the strange quark and anti-strange quark have the same magnitude but opposite charge. Up and down quarks and antiquarks simply have a strangeness of 0. In other words, they have no strangeness. So going back to our up, down, anti-up and anti-down quarks, if we examine their strangeness...
I do not approve of this literal. Down quarks have no strangeness. When it really seems like literally the difference between a down quark and a strange quark is that they are seeing some additional feature to the down quark that they then label as strangeness. I don't know why, it has different features, so it's a different particle, period, to the end. Like, what the? I don't know if this makes sense, even in a world of quarks existing.
Yes, we find that they all have 0 strangeness.
Obviously, this is my ignorant first impressions.
So they have no strangeness. We can summarize the strangeness of each quark in a table along with charge. So we saw previously how we summarized the charge of each of the quarks in a table, and we can do the same thing for their strangeness. So we saw for up, down and strange quarks, they have charges of +2/3, -1/3, -1/3 respectively. And now if we look at their strangeness, we've said up and down quarks have no strangeness, so their strangeness is 0, and the strangeness of a strange quark is -1. Similar to charge, the strangeness of an antiquark is the same magnitude, but with the opposite sign of its corresponding quark. So again, we can summarize the charges. We said an anti-up quark has a charge of -2/3, anti-down has a charge... If you're looking for...
Okay, that was fine, whatever. Is this the next one? Yes, okay.
Hi guys, in this video we're going to be looking at antimatter, antiparticles, and we're going to finish off with a summary.
So first of all, we're going to discuss something called antimatter and understand what antimatter is. The universe is composed of matter. So everything in the universe is...
We are composed of matter.
It's made out of matter. So for example, the sun, this kettle here, and this football, they're all made from matter. The matter that they're made from is very different, which is why they all look different, why they have different properties. However, they're all made from matter. Matter takes the form of particles, such as protons, neutrons, and electrons. So, for example, this here is a proton, this particle is a neutron, and this particle is an electron. So all three of these are particles. So they're different types of particles, but they're all considered particles. There are also other matter particles we will encounter, such as the neutrino. So this particle here is a neutrino. Matter particles are formed in matter-antimatter pairs from large amounts of energy. So here we have some energy, And this large amount of energy can actually form a matter and antimatter particle pair. So this is before the pairs are formed, and then afterwards we can actually form two pairs. So this particle here makes up matter, so it's a matter particle, and this particle here is antimatter. However, even though one is matter and one is antimatter, they're still both particles. In each pair, there is one particle of matter and one particle of antimatter, called an antiparticle. So this here is a particle, and particles make up matter. So for example, like we saw, the sun is made out of matter, a kettle is made out of matter, and a football is made out of matter. And then this other particle here is an antiparticle, and this antiparticle is what makes up antimatter. And we can't actually see this antimatter, however we know that everything else in the universe that isn't made out of matter is made out of antimatter. So now we're going to look at the different types of antiparticles in a bit more detail. Every particle has a corresponding antiparticle. So for example, this here is a particle, and this other particle here is an antiparticle. So it makes up antimatter. An antiparticle has the same mass, size, and magnitude of charge as its corresponding particle. So this here we said is our particle, and this is our antiparticle, and they both have the same mass, so if we weigh them we get the same mass. They're also the same size, so that also tells us they must have the same density, and they also have the same charge magnitude, so the size of their charge is the same. The only known difference between an antiparticle and its corresponding particle is an opposite electric charge. So we can see here that we have a particle and an antiparticle, and they have opposite charge signs. So one is positively charged and one is negatively charged.
Okay, charge, electric charge. It's pretty simple. Positive charge, out arrows away. Negative charge, arrows in. Essentially, every particle exerts an outward pressure, and then the ether exerts an inward pressure, and the balance, if there is a balance, produces the outcome. So if it is in balance, essentially, where the outward pressure and the inward pressure are equal, then the particle is neutral. But if the outward pressure is less than the pressure flowing inward, then it becomes a negative charge particle, and vice versa. If it's a higher pressure by the particle exerted relative to the environment, then it is a positive charge. And so there is a physical flow of particles going on that is producing the differences. And so when it comes to antimatter and matter, that there is an opposite charge, but the same mass is present, and the same size. Essentially, what I think is going on is like a particle matter is taken out of the 0 point energy, and so like a vacuum occurs. So basically a matter, like a star, it takes in infinitesimal particles that cause gravity, and then it recycles them into larger particles, and then it radiates larger particles of radiation. So it's a star because it's massive and it's radiating. But there's the possibility that if you reverse time, so antimatter is just the same particle, but with time reversed, interestingly. If you reverse time for a star, then it's not radiating, it's actually taking these particles in and then breaking them down and radiating tiny particles. And so basically it's a high density of tiny particles versus a high density of larger particles that occurs between like a vacuum particle, which is antimatter, versus matter, which is like a, as we know it, type of particle that's solid and dense, made of matter, not of a vacuum. But the reality is it's just a vacuum with time reversed. Is a star because we are composed of atoms, which then determines the way in which we observe time, because our atoms function in a certain way, which then directs the flow of time because we're made of matter. But that's just how we see it, in the same way as there can be a particle, like Earth can be seen as the nucleus of an atom, so too can antimatter be seen as matter, and matter be seen as antimatter to an observer literally seeing time in reverse. It doesn't conglomerate with matter, it conglomerates with antimatter in the vacuums of space, and that's where it is. And that's when we're like, where is the antimatter? Why is there this imbalance? It's because it separates itself. I mean, sure, they mesh just because it's not truly like annihilation occurs, and that's the end of the story, and that's that, because we can observably contain antimatter using a magnetic field, which means that magnetic fields, which are composed of particles, are able to interact without some like form of annihilation of the particle occurring, so they're not inherently that way. Okay.
Because they have an opposite charge, this means they experience an electrostatic force of attraction. And this is because we know opposite charges attract each other. For example, the antiparticle corresponding to the electron is the positron. So here we have an electron, which we know is a particle, and then the antiparticle of the electron is the positron. So since it's an antiparticle, it makes up antimatter. Positrons have the same mass, size, and same magnitude of charge as an electron, but their charge is the opposite sign. So we said this here is the electron, and then this particle is a positron. So an electron has mass 9.11 times 10 to the minus 31 kilograms. And this is also the mass of the positron. Their radius is equal to 2.82 times 10 to the minus 15 meters. And finally, they have the same magnitude of charge but opposite sign. So an electron has charge equal to minus 1.6 times 10 to the minus 19 coulombs, whereas a positron has a charge equal to plus 1.6 times 10 to the minus 19 coulombs. So we can see the size of the charge is the same, it's 1.6 times 10 to the minus 19, however the sign is different. We can represent the particle-antiparticle pairs with symbols. So for our electron, we use the symbols E minus, beta minus, and also just E. Then for our positron, the corresponding symbols are E plus, beta plus, and E bar to represent the antiparticle. So these are all different symbols that we can use, but any of these symbols are appropriate. We can summarize the main particle-antiparticle pairs in a table. So for example, let's go back its particle pair. So we said that the symbol for the positron, so a positron is the proton, so its symbol is P bar. We know, and the neutron has an N bar. So we know that an antineutron is going to have a pair with 0 mass. Neutrino, it's going to have a symbol V, also has 0 mass. Particle antiparticle pair we're going to look at charge. And finally, an antineutron is going to have the same mass as a neutron.
Zero mass. Zero mass, zero mass, zero mass, huh? Okay, here we go.
Called hadrons and leptons, depending on their properties. So here we have lots of different types of particles, and these particles can be put into 2 different groups, one of which is called hadrons, so that's one type of particle, and the other type of particle is called leptons. One of these groups are the hadrons. So these blue particles here are the hadrons, and they're one type of group. Hadrons are particles and antiparticles which can interact through the strong interaction. So the strong interaction is the same as the strong nuclear force here. So we know that the strong nuclear force is acting within the nucleus of an atom. So that's what we have here, the strong nuclear force. And since the particles in the nucleus interact through the strong interaction, we can call these particles hadrons. And particles which don't feel the strong nuclear force aren't hadrons. All hadrons are able to feel the weak nuclear force. And this makes sense because if we...
So frustrating. Strong interaction, just there it is. Oh, okay. Through what now?
All hadrons are able to feel the weak nuclear force.
And the weak nuclear force. I might have already talked about this in previous videos, to the point where that made sense that they would even just say it like that, but certainly not in the particle physics, and then it just kind of goes to other stuff. So maybe not.
And this makes sense because if we...
There's just no reference to how we got here. Just here we are. This is how things are now.
We said that the only particles that are hadrons are ones that experience the strong nuclear force, and the particles within the nucleus experience the strong nuclear force, then it makes sense that they also experience the weak nuclear force. So they experience the weak nuclear force within the nucleus. And we've said that the weak nuclear force is responsible for processes and changes within the nucleus such as beta decay. All hadrons are also able to feel the gravitational force. So we've said the gravitational force is the force that attracts masses. And both protons and neutrons, which are within the nucleus, have mass, so they therefore experience the gravitational force. And we're using protons and neutrons as examples here of hadrons because they make up the nucleus, so they experience the strong nuclear force, and they have mass, so therefore they also experience the gravitational force. Hadrons will also feel the electromagnetic force if they are charged. So for example, we can consider a proton and its antiparticle, the antiproton. And both of these particles are charged. So the proton is positively charged, the antiproton is negatively charged, and since they're charged, they experience the electromagnetic force. So this means that protons and neutrons are both hadrons. We've already mentioned that protons are hadrons because they experience the strong nuclear force, but now let's just summarise what they make up the nucleus.
I wasn't especially listening.
And both protons and neutrons, which are within the nucleus, have mass, so they therefore experience the gravitational force. And we're using protons and neutrons as examples here of hadrons because they make up the nucleus, so they experience the strong nuclear force, and they have mass, so therefore they also experience the gravitational force. Hadrons will also feel the electromagnetic force if they are charged. So for example, we can consider a proton and its antiparticle, the antiproton. And both of these particles are charged. So the proton is positively charged, the antiproton is negatively charged, and since they're charged, they experience the electromagnetic force. So this means that protons and neutrons...
It just occurred to me, I don't think I mentioned that the Earth expanded much more recently and that the dating is wrong because we assume constant decay rates across time and then use that as a method to determine how old the ocean floor is, and that's all there is to it, without recognizing that decay rates are not constant and there's evidence that just seasonally they change. So if the Earth were to have literally undergone a process of decay, it would probably appear as if there was large amounts of decay that occurred relative to when it's not expanding because it's not in the process of decay, and so it doesn't really have detection of decay. And so when we measure how much decay occurred based on today's decay rate, looking at the ocean floor, then it's going to look like a long time passed, but that doesn't make it so. Anyway, I just want to bring that up because I don't think I pointed out the evidence, and I was like, I'm sitting here saying something, I didn't even point out that. I know I have a basis. Just sloppy. Not to call this sloppy, just the way quantum mechanics has evolved across time to not need to explain how we got here. Now it's just pretty much, this is what it is, and just shut up and calculate and stop asking questions that we don't have answers to because we don't know what we're talking about. Maybe I don't know. I'm sorry, guys.
are both hadrons. We've already mentioned that protons are hadrons because they experience the strong nuclear force, but now let's just summarize why they are hadrons. So if we think about the forces that are felt by a proton, we know that it feels the strong nuclear force because protons make up the nucleus and the strong nuclear force keeps the nucleus together. We know they experience gravity, and that's because protons have mass, and gravity is the force that attracts masses. We also know that they experience the weak nuclear force because protons can undergo beta decay within the nucleus to form neutrons, and the weak nuclear force is responsible for beta decay. And we also know that protons experience the electromagnetic force because a proton has a positive charge. But the key force here that tells us that a proton is a hadron is the fact that it experiences the strong nuclear force. So we can therefore conclude here that a proton is in fact a hadron. So now let's do the same for a neutron. So let's consider the forces felt by a neutron. So we know that a neutron is going to experience the strong nuclear force because, again, neutrons make up the nucleus and the strong nuclear force keeps the nucleus together. The neutron also experiences gravity because, again, it has a mass and gravity is the attractive force between masses. And finally, the neutron also experiences the weak nuclear force because it can undergo beta decay within the nucleus. It doesn't experience electromagnetic force because it's neutral. However, it is not essential that a hadron experience the electromagnetic force. It only experiences the electromagnetic force if it's charged. So since the neutron does experience the strong force, we can therefore conclude that it too is a hadron. So we can see that both our particles that make up the nucleus, the proton and the neutron, are hadrons because they both experience the strong nuclear force. Hadrons are composite particles. So here we're looking...
They just redefine things that are already defined and make it confusing for no reason. They're protons and neutrons. Why are there suddenly a whole fucking class of particles, hadrons, that need to be explained? And this is why they're hadrons, and then the main reason why they're hadrons is because they experience...
So since the neutron does experience the strong force, we can therefore conclude that it too is a hadron.
Also hadron, boom. See? They experience the strong force. That's how we differentiate ones that experience the strong force. Hadrons. If they don't experience it, they ain't hadrons, dude. That's some universality right there. Thanks for wow.
You can see that both are particles that make up the nucleus, the proton and the neutron, are hadrons because they both experience the strong nuclear force. Hadrons are composite particles. So here we're looking at a neutron, and we've just said that a neutron is a hadron. So a hadron is something called a
made up of quarks.
particle.
And made up of
But what do
quarks.
you mean by composite particle?
Well, it's made up of quarks, you
This
see.
means that they're made up of
I gotta fucking get past this.
split up into leptons.
I can't
So
take
we
it.
know that we can group particles into two groups depending on their properties. So here we've got all our different types of particles. And one of these groups are the leptons. So we've looked at hadrons, and now we're going to look at the other group of particles, which is the leptons. Electrons, neutrinos, and their antiparticles are examples of leptons. So for example here, we've got the electron, which is a lepton, and also its antiparticle, the positron, is a lepton. And we've also got the neutrino, which we've said is a massless, chargeless particle. And we've also got the neutrino's antiparticle, which is the antineutrino. And all four of these particles are leptons. But what are leptons? Well, leptons are particles and antiparticles that cannot experience the strong nuclear force. So, if we were to consider protons and neutrons, we know that they make up the nucleus, and therefore they experience the strong nuclear force because this is what keeps the nucleus together. So this tells us that protons and neutrons can't be leptons. And that's because both protons and neutrons experience the strong nuclear force, however leptons are particles that can't feel the strong nuclear force. All leptons are able to feel both the weak nuclear and the gravitational force. So for example, we're going to consider the electron and the antineutrino, and we've seen that the electron and the antineutrino are both involved in beta decay. And beta decay is when a proton or a neutron changes within the nucleus. So since they are part of beta decay, this tells us that the electron and the antineutrino both experience the weak nuclear force. And we can also consider the electron and the antineutrino and whether they experience the gravitational force.
God.
So they both also experience the gravitational force, which is why they are classified as leptons. So both the electron and the neutrino experience the gravitational force, and that's because they're attracted to other particles. Lepton particles that have a charge will also be able to feel the electromagnetic force. So going back to our electron, because we know an electron has a negative charge, if we were to consider the interaction between a proton and an electron, they would attract each other because of the electromagnetic force and because they're both oppositely charged. So this shows that the electron, which is a lepton, can experience the electromagnetic force because it's charged. Leptons are something called fundamental particles. So this electron here, we've said, is a lepton, and this means that it is a fundamental particle. And this means they cannot be divided into smaller particles. So a lepton can't be broken up into smaller particles.
Oh my
So
God.
leptons aren't made up of further particles. They make up other particles.
We don't need quarks to explain these particles. So we're just not gonna have them involved here. These are fundamental plus the quarks. Boom, let's see. Standard model of physics. Yep. So these are not composed of quarks because we don't need quarks to explain them. Okay. I see. Nonsense. Even the dude who proposed quarks was like, I don't know, guys. Oh, yeah. Oh, dude, that's totally it. That's it. Let's go with it for the next 50 years. Without any resistance. There's no resistance in the physics community for this fucking just... Where are we going? Did I just watch that one? I just watched that one. Okay. Baryons.
Hi guys! In this video we're going to be looking at baryons. Baryons is quark combinations, and we're going to finish off with a sum.
So first of all, we're going to talk about a type of particle which is called a baryon. All particles can be divided into hadrons and leptons. So we've seen previously the two main groups of particles are hadrons and leptons. And we know that a proton is a type of hadron, and we've also seen that an electron is an example of a lepton. And we've had a look at leptons in quite a lot of detail. However, hadrons can be further divided into baryons and mesons. So the group of particles that we've encountered, which is the hadrons, they can actually be further divided into two other groups of particles. And these two groups are called baryons and also mesons. Baryons are defined as hadrons that are made up of three quarks. So for example, this here is a baryon.
What are some other...
So you can see
what is the exhaust... Why are there two particles? That's all we fucking list. Proton, neutron. What is the exhausted list? Is it proton, neutron, antiproton? Maybe even anti-neutron.
Made up of three quarks. We have an up quark.
Full list of baryons. Oh my god. Okay, that's why it's only protons and neutrons. It's just a bunch of fucking bullshit that probably lasts for a microsecond and they're fucking putting up mean lifetime. Oh, this one's got... This one, oh, it's a neutron. So yeah, that one's actually a reasonable amount of time. Oh, yeah, that's because it's a fucking neutron. I see, that's interesting. It's not nearly as stable as a proton. Literally everything else is 10 to the minus 10 or less. Oh my god, guys. And then you're gonna list these as equivalents. Although it's interesting to consider that maybe they are like, they would be equivalents if in a higher energy. Like protons and neutrons are only stable on Earth, in the Earth environment. And then beyond that, maybe there's a difference, like subtly larger particle, like suddenly this charmed lambda or sigma particle is like stable, and the proton and neutron is unstable and can't exist well there. Or maybe like because like the proton is in such a higher energy environment that it's not just, it drops to neutral, and the neutron, I guess, I don't know, the proton even goes to negative, becomes the electron in some other place. Because it would effectively be, if it's in an environment that essentially is a high enough pressure where the particle then is a negative particle because it's just a matter of pressure balance. So since the proton is a proton is a proton is a proton, it's going to exert a pressure outward while it's a proton, at least, until the environment changes, let's say, to a higher pressure. Then it becomes a plasma, or it's neutral. It doesn't even need like on the sun, protons are neutral. They don't need a electron to exist at all. Why is that? Because the pressure of the environment just makes it imbalance. It doesn't need that extra electron anymore. It's not because it's some inherent characteristic thing, charge. So now I'm looking at this, none of these particles. So like, example, the only examples ever going to be listed, maybe the sigma, I guess, but like looking at this list is kind of a joke, honestly. What are we doing? Up, down, B, bottom. Beauty quark. Charm, strange, oh my god. Like this shit, is this almost entirely theory and based on crashing particles together and thinking that we can describe what we're seeing with this fucking shit? What is going on?
And 2 down quarks. So since we've got 3 quarks, we can classify a neutron as a baryon. For example, protons...
I really do not like this. Since we said that they were made up of 3 quarks, since
3 quarks, we can classify a neutron as a baryon.
Oh, good.
For example,
good.
Protons and neutrons are both made up of 3 quarks, thus are both hadrons. So a proton is made up of 2 up quarks and a down quark.
Yes,
and we've just said that a neutron, the lightest baryon, this tells us that protons are the most stable. And if they're the most stable baryon, baryons. And because protons are the lightest baryon, this tells us that protons are the most stable. And if they're the most stable baryon, this means that all baryons are eventually going to decay to protons because they're the most stable type of baryon. Antibaryons, such as antiprotons and antineutrons, are made from the antiquarks of their corresponding baryon quark composition.
That's interesting.
So here we have a baryon.
And it's kind of what it's suggestive that even the neutron decays into the proton, but where the flow of things is towards stable is a positive for baryons. And maybe leptons stable is an electron,
which is our neutron. And we said our neutron is made up of 2 down.
a list of, is this all of them? Electron, oh, okay. Just the electron, and then like its larger cousins, which is interesting. It's almost like different octaves. Sometimes I try to look if there's like a tendency in the mass change to suggest of an octave. I don't know what the pattern is. Might be a pattern decipherable if we really look into it enough. Consider it a possibility. That's probably there. Lepton, what else? Okay, so it's the 6 and then the mirror antiparticles. Okay. Apparently an electron neutrino is stable. A muon neutrino is stable. Where is this stable? Lifetime. Muon is not stable. Tauon is not stable. Muon is significantly more stable than a tauon. But apparently, muon neutrino 0.19. Those values are not things. Charge lepton number, whatever that means. E something T.
Quarks and an up quark. But now we're going to look at an antibaryon.
Okay, fine.
And the antibaryon we're going to look at is the antineutron. So we know that the corresponding antiquark for a down quark is the anti-down quark. So we've got two anti-down quarks here, which make up the antineutron, and the antiquark for our up quark is going to be the anti-up quark. So we can see here that our neutron is made up of two down quarks and an up quark, two anti-down quarks and all other hadrons that will eventually decay to become protons. So as we said, the proton is the most stable baryon because it's got the lowest mass. So all other baryons want to decay to become a proton. So, for example here, we have a neutron.
Proton is the most stable. Everything wants to be protons. Certainly is observer dependent. We see hydrogen as the most stable, probably for a reason. Like whatever it is that someone observes as the most stable, they will see as protons.
And this is a baryon that's going to decay to a proton. And when the neutron decays, it undergoes beta decay. And when it undergoes beta decay, it produces a proton along with an electron and an antineutrino. This means that baryons all have a mass greater than or equal.
I love that it produces an electron and an antineutrino, but it just has quarks.
To the mass.
Significantly more evidence that it has an electron and an antineutrino within it than that it has quarks within it, in my opinion.
Of a proton. So here we have a proton and it has its corresponding mass. And since we've said that the proton has the lowest mass out of all the baryons, this tells us that all baryons must have a mass greater than or equal to the mass of a proton. So now that we understand what baryons are, we're going to look at baryons as quark combinations. The quark composition of a baryon is what gives it its property. Two up quarks and one down quarks, and we can just add it on we can use this to of the individual quark charge. And our final plus 2/3, the charges of its constituent quarks have charges of plus 2/3, and then the down quark a neutron is made up of just in terms of the individual charges of its constituent quarks. So its total charge, separate the sub...
Just here's our fucking theories. Quarks, 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 and quarks.
Charge, then we're going
really
to
don't agree.
Neutron.
These videos are not trying to teach where we're coming from.
Divided into two other groups, one of which is the baryons, which we've already looked at, and the other group is the mesons, which is what we're going to look at in more detail in this video. All particles can be divided into hadrons and leptons. So we've seen that the two main groups of particles are hadrons and leptons, and a proton is an example of a hadron, and the electron is an example of a lepton. We know that hadrons can be further, and the electron is an example of a lepton. We know that hadrons can be further divided into baryons and mesons. So hadrons, one of the main groups of particles, are actually further divided into two other groups. And these groups are called baryons, which we've already looked at in more detail, and mesons. Mesons are composed of two quarks, specifically a quark-antiquark pair. So here is an example of a meson, and we've got a...
So basically, there's up and down quarks, and that makes up proton and neutron, which is the only particles that really matter. And then a bunch of things that we see for a millisecond in time, which we then tried to explain also as if they're real particles of equal significance and things, instead of just and then suddenly we got a real complex system of quarks to explain all these particles. I mean, it's a little concerning.
Down quark along with an anti-down quark. So we've got the down quark here. So this is the type of quark. And then we've also got the down quark's antiquark. We can consider the antiparticle of a meson by replacing its quarks with their antiquarks. So we've just looked at a meson made up of a down quark and also the down antiquark. So for example, if we swap the down quark here for the down antiquark, and the anti-down quark for the down quark, we end up with the antimeson. We see that a meson antiparticle is a quark-antiquark pair, and therefore is still a meson. So we've just worked out what the antimeson is of our original meson, and we saw that it's made up of an anti-down quark and a down quark. So therefore, it's actually got the same composition as the meson we looked at. So we can see that the antimeson is also a meson. So especially, a meson is its own antiparticle. So going back to our antimeson, we've said it's equivalent to the original meson we were looking at, because it's still made up of a down antiquark and a down quark. So we can see that it's got the same composition as the original meson, so its own antiparticle. Another way to define a meson is as a particle which will never decay into a proton, or into any particles that could subsequently decay to a proton. So what we're saying here is that our meson cannot decay into a proton. So it therefore can't be a baryon, because we've said all baryons are either protons or particles that can decay to become a proton. And our meson also can't decay into a particle that could subsequently decay into a proton. So for example, it can't decay into a neutron, and then a neutron decay into a proton via beta decay. So this is also not possible. So again, this confirms that mesons aren't baryons, they're their own group of particles. So if mesons can't decay into protons, this means that mesons always have less mass than a proton. So if we look at the mass...
Oh my god, it's so ridiculous.
...mass of a meson and compare it to the mass of a proton, we can see that the mass of the meson is always less than the mass of a proton. Because if it was greater than the mass of the proton, then it would be able to decay to become the more stable particle that is the proton.
So they're like partial.
In fact, mesons are intermediate in mass between an electron and a proton. So if we compare the mass of an electron with the mass of a meson and the mass of a proton, we find that the proton has the greatest mass and the electron has the smallest mass. So the mass of a meson comes somewhere in between the two.
Of course
there are two types of mesons which are common in interactions: the pion and the kaon. So here we have our pion, and this here is the kaon.
Literally, of course it does though.
So these are the two most common mesons that we're going to look at.
Like, it makes fucking sense that there's particles there. They probably don't exist for long, because it's not stable. Let's see. List of mesons. Let's see. Oh my god. Lifetime. Ridiculous. Literally 10 to the minus 8th seconds. 10 to the minus 8. Oh my god, guys. This is absurd. Fucking absurd.
And both of these mesons can be either positively charged, negatively charged, or neutral, so they have no charge.
Okay.
So now that we understand what mesons are, and we've seen that there are two specific types of mesons, the pions and the kaons, we're going to look at pions in a bit more detail. One class of mesons are called pions. So what we can see here is our image for a pion, and this pion is just a type of meson. We can represent the pion with a symbol. So the symbol we use for a pion is the Greek letter pi. There are three types of pion. So we've got the positively charged pion, and this has symbol pi plus. So the plus here represents that it's positively charged. We have the negatively charged pion. So this has symbol pi minus to show its negative charge. And finally, we have a neutral pion. And this has symbol pi naught. And this represents that it's got zero charge, so it's a neutral particle. All pions, or pi meson, pi plus, so the plus here represents that it's positively, we have a neutral pion. And this has symbol pi naught, and this represents that it's got zero charge, so it's a neutral particle. All pions, or pi mesons, have a mass greater than a muon, but smaller than a proton. So if we compare the masses of a muon, a pion, and a proton, we find that the proton has the greatest mass, then the pion has the next greatest mass, and the muon has the smallest mass out of these three particles. We can work out what kind of pion a given particle is from its quark composition. So for example, here we have...
She just threw the muon in.
greatest mass, then the pion has the next greatest mass, and the muon has the smallest mass out of these three particles. We can work out what kind of pion a given particle is from its quark composition. So for example, here we have a down and an anti-down quark composition for this meson. And using this quark composition, we can work out what type of pion this is. So what we mean by type of pion is whether it's a positively charged one, a negatively charged one, or a neutral pion. So we're going to use the quark composition to work out the charge. So let's try this out in an example. What kind of pion is a meson consisting of a down quark and a down antiquark? So the composition of this pion here is a down quark and a down antiquark. And we know that a down quark has a charge of -1/3. And a down antiquark has a charge of +1/3. And that's because they have charges of the same magnitude but opposite sign. So our first step is to write the equation for the total charge of the pion in terms of its -1/3 of 0. So we can see that this pion is the neutral pion with symbol pi naught. We actually have 3 different quark compositions for neutral pions. So we've just seen the composition where we have a down quark, these 2 compositions as well. So the charge for the up quark, up antiquark composition is given by plus pion. So here we have a pion with a down quark pion. So meson we're going to use for our kaon,
Oh my god, it's fucking ludicrous. Straight ludicrous.
And again, this is just a type of meson. And as we've represented all the other particles we've come across so far, we can represent the kaon with a symbol. So the symbol we use for the kaon is just a K. And there are three types of kaon. So we've got a positively charged kaon, and we represent this using the symbol K+, the plus representing its positive charge. We have a negatively charged kaon, and this is represented with the symbol K-. And finally, we also have the neutral kaon, and this is represented with symbol K0 to show the zero charge. The kaon, or the K-meson, has a mass greater than a pion, but smaller than a proton. So we're going to compare the masses of a pion, a kaon, and a proton. So here we have a pion, and here we have a kaon. So out of these three particles, the proton has the greatest mass, and the pion has the smallest mass, so we can see that the kaon's mass comes somewhere in between the two. As with pions, we can consider the quark composition of the kaon to determine its type. So for example here, we've got a down quark and an anti-strange quark, and that makes up our quark composition for this kaon. And using this quark composition, we can find out the charge of this kaon and therefore determine its type. So to the quark composition, our first step is to write the equation for the total charge of the kaon in terms of its strange antiquark. Kaon is going to be so we've got we can represent it with the symbol K0. The kaon with the down antiquark and strange, we know that, so therefore our overall
Hi guys, in this video we're going to be looking at types of radiation, alpha radiation, beta radiation, gamma radiation in magnetic fields, and then we're going to finish with a summary.
We're going to discuss three different types of ionizing radiation. Ionization is the process of removing an electron from an atom to produce a positively charged ion. So here we have an atom, and if an electron is removed from the atom by the process of ionization, it forms a positive ion. We can cause this ionization of atoms by using something called ionizing radiation. Here's an example of a type of ionizing radiation, which will cause an electron to be removed from the atom and create a positive ion. Ionizing radiation is radiation that can ionize atoms by removing some of their electrons, leaving positive ions. There are three types of ionizing radiation that can be distinguished by their different properties.
Enough. Oh my god, look at this. I viewed like every video. Sure.
So we just explained the electromagnetic force.
It's a little fast.
And the way that transfer momentum through these exchange particles, these virtual exchange particles, the photon. We say that the exchange particle for the electromagnetic force is virtual photons. We need a force to explain beta decay. So we okay with gravity, that's the force that attracts mass to mass. We okay with electromagnetism, that's the force that either makes charges repel or attract each other depending on the sign of the charges. We're okay with a strong nuclear force, and that's the force that holds nuclei together in a nucleus. But what's causing beta decay? Where we have this neutron here, decaying to this proton here and emitting an anti-neutrino and an electron. This electron being the beta minus particle. So there's...
Okay, neutron becomes proton, emits those things, yep, that's good, fine. Okay.
Definitely something going on there. Remember, this would be beta minus decay here. There's definitely something going on here. There must be some force that's responsible for this. And what is that force? Well, it can't be electromagnetism.
There must be a force. It must be a new one.
We were just discussing, because neutrons are neutrally charged. This particle has a charge of 0, so how is it? What's going on here? It can't be that. It also can't be the strong force because we know what the strong force does. It's what's responsible for binding protons and neutrons in the nucleus. It can't also be making neutrons decay into protons or whatever. It can't be that. So it must be a new force. We call the weak nuclear force.
There it is. Oh my god. The line of reasoning. Literally, because fuck philosophy. It must be something new we haven't figured out yet. We'll just add some more shit on top. Then there's this, then there's this, then there's this, this. Dudes. This process, it's important to understand that when a star supernovas, all of its atoms radioactively decay simultaneously because it literally is radioactive decay. So if you want to know what's causing beta decay, what's causing supernova, I thought we already figured that out as being gravity. Maybe we just don't quite understand what's going on. This is definitely concerning when it's just, that's how we think about it. Like I said, it must be a new force. We'll call it the weak nuclear force. Why? Because it's weaker than the other one. One of them's nuclear, it's strong, it holds the protons and neutrons together, so that's a pretty strong one, according to how much strength is required, and then the other one doesn't require as much strength, so we'll call it weak.
Why do we call it the weak nuclear force? Well, it's kind of just in the name. It's weaker than the strong nuclear force. It has to be, otherwise it would affect stable nuclei. For instance, we were saying that it only works when we've got these radioactive forces, these radioactive particles, they decay.
Yes. Radioactive particles, which are unstable because they're exerting a pressure that's higher. So like the periodic table of elements, lower particles like hydrogen are just simply not exerting as much pressure outward on the ethereal environment as higher molecular weight particles like uranium, which exist in the same ethereal environment as those hydrogen atoms. And so because the environment is the same but the particles are different, then the outcome is that the higher mass particles, which are therefore exerting a higher pressure outward, are less stable and more likely to literally supernova because of that instability. Although that's one way.
Any particle, if the weak force was stronger than the strong nuclear force, then any particle always would decay. Whereas as it is, it only affects particles with unstable nuclei. And that's what gives us this beta decay. This was our unstable nucleus. And then that's what decays, and actually what we have happening in here is a neutron changing into a proton. Obviously we can't see that because we're in the scale of looking at a huge nucleus, and I couldn't possibly draw so many protons and neutrons together. But the idea is that somewhere in here a neutron is changing into a proton, and that's what's emitting this beta minus particle and this anti-neutrino. But that only happens for radioactive particles, right? It only happens for unstable nuclei. It certainly doesn't happen for all nuclei, otherwise the world would be a very different place. And so that's what means it's weaker than the strong force. And it turns out there are many, many weak interactions. So we just literally looked at one here, beta minus decay of a neutron into a proton, but there's many more. And we're soon going to meet some more. For instance, we've seen beta minus decay, but there's also beta plus decay, so positron decay and others. So we're okay with the idea that forces, or at least we've seen one example, electromagnetism here, where there is an exchange particle, this virtual photon.
Hey guys.
This one tended to be the best one I could find on this. They're all trash. No, not trash, just like the fucking explanation is simply not good. Let's see what this dude says. Genevieve.
In this sixth module, we are discussing weak interactions, and in this third video, we will go through the general properties of weak interactions, which are not quite like the others. After following this video, you will know about the non-conservation of parity for weak interactions and the main vertices and charges which are relevant. Weak interactions, in fact, do not deserve their name. Their apparent weakness at low energy is due to the fact that they are transmitted by heavy particles, the neutral Z and the charge W plus W minus bosons. Their propagator weakens the amplitude at low momentum transfer.
Oh my god. Stop fucking confusing things. Obviously, this is just nonsense. Literally. Like, it's probably an electron that was in a certain stable state that then unstable state. It was stable within the system, but then when it was ejected from the system... Why is that arrow that way? This W boson ejected from the system, not stable without being an electron, because it's ultimately stable as an electron in our environment. So it decays, releasing another particle, which then makes it actually stable as an electron. I do think that this is what happened to Mercury, where it was released by the sun, became one of its electrons, shrank in the cool environment comparatively, and ejected a particle that came out of its surface and left if this is something that's going on. Where is it? I don't know where it is. This one, I believe. The way these are, these could have just been like particles ejecting as it decayed that were literally kicked out of the nucleus of the planet through the walls, creating these structures initially. I don't know why it would just be 1, 2, 3. Maybe because there's more subtlety to what's going on than we realize, if that were to be a thing. I just had this thought the other day, yesterday even, maybe, like, oh, what if? Watching a video on Mercury while in the midst of going through this kind of stuff, trying to be like, is this real? Like, what is actually observed? What is actually observationally observed here? What do we know that we can say? Because it sounds like we can't even say quarks are known. You know, I really trusted you guys to have some basis in what you were saying, where when I went into it, I want to be like, wow, there's literally no reason for these quarks to exist. They just assumed them. Oh, they work well. Ain't that fortuitous for the model? Go on and on and on. Where anything new, we just need to add a new kind of quark and explain, oh, this quark has this new feature, so that the particles are then like in this other way also. There's this other way that things could happen where, because there's other quarks, there's a super quark. Maybe I shouldn't call it an S because that's strange. There's up, down, so S, D, C. Yo. I got nothing.
Their coupling constant G and G prime, on the other hand, are of comparable magnitude as the electric charge E. Indeed, they are connected by the condition of electroweak unification, which involves the Weinberg angle theta W. Its value is close to 30 degrees, so instead of 3...
So up becomes down and releases the W boson. I'm not sure what this is about. Why this is in? I thought like this becomes two particles, like both out. I don't know. This one.
Coupling constant, there's only one and an angle. The tangent of this angle is the ratio.
Who's explaining it I'm not listening? I'll be back.
In 1956, a team of scientists was working on an experiment that at first glance seemed kind of trivial. They had lined up a bunch of cobalt atoms and were patiently waiting to see which direction they would spit out some electrons. According to the knowledge at the time, the electrons should have come out in random directions, but that is not what happened. Instead, the electrons tended to favor a specific direction. And to me, and probably you, this doesn't seem like that big of a deal, but the implications of this tiny, quiet experiment were groundbreaking. Because these results weren't just about some specific atoms, they challenged one of our fundamental beliefs about the entire universe, and ultimately opened the door to some of the biggest mysteries in physics. Here's why this little experiment turned out to be such a big deal. The reason these results threw physicists for a loop is because they violated something called parity symmetry. At its heart, parity symmetry says that the laws of physics shouldn't differentiate between left and right, or up and down, or backward and forward, because really, those directions just depend on your perspective. Take gravity, for example. Like, normally you would say that gravity pulls things down, but of course, we only call it down because that's where gravity is pulling things. If you change your perspective and stand on your head, that doesn't mean that gravity is going to start pulling everything like down toward your feet and up toward the sky. It's going to keep pulling stuff toward the earth no matter what direction you say that is. And if that sounds obvious, well, yeah. For decades, parity symmetry was this very reasonable, inarguable thing. One that physicists had used countless times to predict correctly the results of experiments. It felt like common sense and was a major assumption we relied on when figuring out how stuff should work. But by the 1950s, some researchers had begun to realize that maybe we shouldn't always be making this assumption. In particular, two researchers pointed out that parity symmetry had been tested, but not in all circumstances. Like, it had never been tested in certain particle decays. So 3 teams of researchers decided to tackle this question, and one of them was responsible for that now famous cobalt experiment. This group was headed by a researcher named Xian Wu, and they studied a type of radioactive cobalt called cobalt-60. When the cobalt decayed, it spat out electrons, and if parity symmetry was true, those electrons should have come out about equally in all directions. It should have happened like this mainly because these atoms are basically sitting still, and you can more or less ignore gravity when it comes to particle physics, so it's not like there's some force on the cobalt that would cause it to decay in a specific direction. Instead, if you did happen to see more electrons coming out in a certain way, it would mean you had a problem on your hands. If, say, more electrons came out of the tops of the cobalt atoms rather than the bottoms, it would mean that electrons, for some reason, had an easier time moving up than down. And according to parity symmetry, there shouldn't be any difference between those directions. After all, what's up from one perspective is down from another. To test if all of this were true, Wu's team used a magnetic field to line up all their cobalt in the same way. Then they set up some equipment to figure out how many electrons came out and in which directions. And the results were a bit of a shock. Instead of seeing the particles come out in random directions, they found that the electrons tended to come flying in the opposite direction of the atom's spin. So if you swapped left and right in this experiment, in other words, if you gave the atoms clockwise spin instead of counterclockwise spin, you would get a different result. You would see the electrons fly out in a different direction, and that's not supposed to happen. These results suggested that there is some kind of fundamental difference between left and right. The universe somehow has a sense of direction. So yeah, something was very wrong with parity symmetry. It didn't exist. Wu's team published their findings in January of 1957, as did 2 other teams that had done similar research on other particles. But just because we had made this discovery didn't mean we were out of the woods. We might have figured one thing out, but now we had opened a gigantic can of physics worms. For one thing, researchers had to grapple with the fact that directions might not be as arbitrary as they once thought, because apparently there is an innate left and right to the universe, which is absolutely bizarre. But they also had to figure out why this happened. What was so special about cobalt that made it act this way? Well, as research went on, it turned out that the cobalt wasn't necessarily the problem. It was something called the weak nuclear force, which is the force that governs how atoms, including cobalt, decay. For some reason, the weak force tends to act differently than the other fundamental forces of physics, and figuring out why is one of the most ambitious projects in the field right now. Because the weak force doesn't just treat left and right differently, it also treats matter differently than antimatter, which we believe should not happen. And it even treats time differently than the other forces, which is exactly as bizarre as it sounds. Scientists believe that if we figure out one more weird thing about the weak force, it could potentially break our understanding of physics. But then again, it could also help us understand why the universe looks like it does. So a tiny experiment from 1956 didn't just affect how we saw a handful of atoms. It taught us that one of the 4 fundamental forces of physics is more strange than we could have ever imagined, and it set us on a path to understanding the laws of the universe, a path that we are still walking down today. But that is a much bigger story, and if you want to learn more about it, we have a whole other video on it, which you can watch right now. And as always, thank you for watching this episode of SciShow.
Just makes me think of quasars ejected from galaxies, from black holes, or they don't have any discussion of it. Nuclear. Maybe that one's on instruction. $42.
The atomic model has remained unchanged for a long time, and yet there are many mysteries that this model has not been able to unlock. Some nuclear reactions are very well known and have been thoroughly studied. One would therefore expect that we know all there is to know about such reactions, and that we understand. How the products are created. One problem is predicting how the larger atoms split. Why does uranium split asymmetrically if the nucleus is simply a collection of neutrons and protons jumbled randomly in the center? If we examine the simple case of an alpha particle emission, this also throws up many problems. One of these relates to the size of the nucleus itself. We know that protons and neutrons have size. This means that the nucleus must have a size which relates to these sizes. If we added to this the fact that in the standard model, the position of the protons and neutrons are thought to be random, then it would imply that to emit an alpha particle, the internal protons and neutrons must rearrange themselves to form this prior to being ejected. This becomes more complex as we examine larger and larger atoms that always seem to produce the same products. The nucleus would need to undergo significant rearrangement in order to accomplish this. And this requires space within the nucleus to allow the particles to move to their correct location. If we examine the width of the nucleus and compare this to the width of the individual particles that make up the nucleus, we find that there is simply no room to allow this to happen. It would appear as if the atoms are in a very dense packing state at all times,
thank you.
which would not allow for any rearrangement of the particles. And this implies that the nucleus must have structure, and this is something that Ido Carr has spent the last 12 years working on, and now has a team of people working on it. Unhappy with the many problems with the current model, he set himself the challenge of redefining the structure of the atom. The basic premise of the structured atom model, or SAM for short, is beautifully simple. The neutron is not considered a fundamental particle. Instead, it is redefined as a proton-electron pair. The nucleus therefore only contains protons and what are called inner electrons. These inner electrons are used to bind the protons together, acting as a kind of glue. In order to bind two protons together, we require one inner electron. One proton and inner electron are therefore equivalent to what was called the neutron. Overall, the charge of the nucleus does not change, but the important point is that the force which holds the protons together inside the nucleus is the electrostatic force, not the strong nuclear force. This also explains why a neutron will decay to an electron and a proton and an antineutrino within 15 minutes of leaving the nucleus, and why the charge of the neutron is zero and its mass is slightly more than that of a proton. The force holding the proton in the nucleus will attract inwards towards the centre of the structure, causing the formation of specific geometric shapes which form platonic solids that have triangular faces, like the tetrahedron and the icosahedron. These form the building blocks from which the larger nuclear structures are built. The SAM team have produced a new periodic table that shows a plausible structural configuration for each element. The structural pattern combined with the plausible structural configuration for each element. The structural pattern, combined with the principle of densest packing, drive the various observable nuclear physics phenomena, including which nuclear reactions are possible, the tendency to fission, and probable isotopic variations that may exist. It is well known that transmutation can occur under laboratory conditions. However, current models are not capable of providing an explanation for how this might occur. The SAM model contains the components for a theoretical basis for the transmutation of metals. This in turn will clear the way for finally resolving the mystery of cold fusion or low energy nuclear reactions. We also think transmutations play a key role in biology, and again here SAM can help understand these vital processes in more detail. One of the main insights obtained from the SAM model is that the inner nuclear structure dictates the chemical properties of the element. Being able to visualize the nucleus can potentially provide structural clues about the outer electron configuration. SAM has also been able to identify several cases of potentially missing elements solely from the vacancies in the new periodic table. They identified structural shapes that can be used to make predictions about the chemical properties of these missing elements. In cosmology, it is thought that the elements are created through a variety of processes in stars. The lighter elements from carbon to sulfur are created by fusion reactions, while elements in the iron group originate mostly in supernova explosions, and elements beyond iron are made in high-mass stars by slow neutron capture and by rapid neutron capture in violent interactions of rare supernova variants or compact stellar collisions. The narrative of the origin of the elements is being challenged by the SAM model. The realization that element transmutation does occur in relatively benign environments suggests that this depiction of nuclear synthesis may be flawed. An alternative possibility put forward by the SAM team is that the heavy elements beyond iron are created in situ on the planets. This would occur in intense electrical discharges. Related to this, electrical discharges are the prime suspect for the occurrence of transmutation in Earth geology. One consequence of this is that the dating of geological layers becomes questionable, since the transmutation alters the decay rate of elements. SAM provides insights that no other model is capable of doing. They explain how each element is structured, why the isotopes of an element differ from each other, where the cycle of 8 comes from, and why it breaks down. It not only explains why elements become unstable after lead, but also why alpha decay happens in some elements and yet not others, and why uranium-235 splits asymmetrically, and the origin of the neutron drip line. SAM is a radically different way of looking at the atom that brings with it a simple approach that is easily understood. Simple rules create the structure of the elements, and these, in turn, determine not only their properties, but also determine how they will interact or break down to form other elements on a predictable basis. The key underlying assumption is simply that the particles are held in the nucleus by one force, the electrostatic force. It removes the need for the strong force and also questions the existence of the many exotic particles that physicists have dreamt up. This is just a brief overview of the SAM model. If you are interested in a deeper understanding of SAM and how it can explain things, like for example why certain elements are unstable, how nuclear reactions would work, how it could explain transmutations, then please see the SAM playlist on my channel, or head over to the SAM website where you can also pre-order their new book.
That was one of the most promising things I've seen in a while. It's almost like the atoms themselves are molecules.
That's one half of the story of electromagnetic charges, electromagnetic attractions and repulsions. That was attraction.
This is such a great talk. Christmas lecture by Frank Close. I've seen this.
Of opposites. Now we've got the repulsions of like charges. And that
All their talks, really. I wonder who did it this last year.
creates a problem for us. Let's just think, we're all sitting here quite happily. Nothing untoward happening to us, not exploding or anything. But inside us are atoms, and in the middle of the atoms are nuclei, and here is an enlarged picture of a nucleus, with lots of neutral particles in it, but also lots of protons, each one of which is positively charged. Now, like charges repel. So each of these protons is repelling all the other protons. The nucleus then should be exploding apart. Yet somehow it stays together. Now that's a puzzle. We'll come to that in a moment and find the answer to it. But first of all, let me give you an idea of actually how strong that repulsive force is. Bryson's next demonstration is going to show us the repulsive power of electromagnetic forces. So, what we're going to do now is first of all cool down this ring so that we make the effect rather more dramatic. And we've got a magnet here which will turn on when Bryson throws the switch, when everything's ready. Okay, don't spill it over me. This is about as cold as, well, the universe out there now. You all ready? Or is it going to be really dramatic by the time it gets going? Right, here it is. Ready to go. Put it on the magnet. Now, turn the magnet on. Okay? Do you reckon we'll try it again? Well done. So, you saw there the power that magnets have got when you can make things repel. In fact, it sent the thing almost as high as I came down from at the beginning, and then it came down rather faster than I did. So, that's the repulsive power that you saw there with a large-scale magnet. Just imagine now, then, the strength of the repulsive power buried in the nucleus. These things are really small, pretty well touching, and each of them repelling with at least as much power as you just saw. So how come we are still sitting here happily without our nuclei exploding apart. There must be something very, very strong here, another force, a very strong force gripping the nucleus together and overcoming that repulsive power. Let me show you what we believe today that's caused by. So here is a picture of a nucleus opened up, and you see the 3 quarks buried inside one of them. And the strong force that binds the quarks together, we show here by these little wiggly lines to give the impression of the thing really being gripped. Now, this force is so strong that it leaks out very slightly. We show this on the outside here, and grips the individual neutrons and protons together. So it's that very strong force, rooted in the quarks, that holds the nucleus together and resists that outward thrust that we saw the demonstration of.
Okay. Enough of that. Enough of that.
A nucleus is a very tiny part of the atom, which is already the plum pudding. Interestingly, it took one of Thomson's own students
Trying to find physics, jet eject. Universe. Cheers, whoa. going directly south too. It's even along the axis of the galaxy. That's interesting. Don't know if we're supernova jet.
Hey everyone, it is Friday, 3 p.m. You know what that means? It's the start of a marathon.
Okay, I'm gonna take a break.